Hi, everyone, and welcome to another episode of Valley of Death. I'm your host, Mo Islam. My guest this week is Brian Barritt, co-founder and CTO of Aalyria, who just this week announced a $100 million funding round at a $1.3 billion valuation. The company, which originally spun out of one of Google's special projects divisions, is building two things that together is essentially next-gen infrastructure for communications. Spacetime, a software layer designed to orchestrate networks in motion, not just users in motion, and Tightbeam, a laser comm system pushing fiber-like speeds through the atmosphere. In this conversation, we unpack why network in motion is the problem behind modern constellations, airborne platforms, and multi-domain defense networking, and why Brian believes we're at the point where it's no longer a technology question, it's an execution and adoption question. A lot to unpack here, so let's get started. Brian, you had a big announcement this week.
Yeah, thanks.
So $100 million at a $1.3 billion valuation. You guys just raised a big funding round, just announced it. Congratulations, first and foremost.
Thank you. It's really exciting. It took a bit, but glad to have it out there.
Well, we're going to dive into that, but in a little bit. But first, I do want to just kick things off. Tell me a little bit of the history of Aalyria. Where does it all begin?
Yeah, kind of begins in two places, two different timelines, and sort of converge. One is kind of our software story, which has its origins in Google in around 2013, when there was sort of a range of projects going on there, trying to connect the unconnected, bring billions of people in the world that lack broadband internet online. And Google was exploring a range of ways to do that, from using satellites in space to unmanned aircraft to novel sort of terrestrial networks. And our software story was kind of born out of that, which we can get into. And then the other story arc kind of begins in the late 90s at Lawrence Livermore National Labs, where there were teams working on making laser communications work well through the atmosphere. And a group there kind of spun out from the lab, and Google saw a need for that technology for some of those things I mentioned earlier that it was pursuing, and acquired that tech into Google. Both of these pieces of tech were incubated there over the course of about 7-8 years, with a lot invested. Some in stealth, some more well-known. And both of those technologies are now part of Aalyria.
So let's, there's two pieces there. There's a software and hardware piece, but let's start with the software piece. So, which is your technology Spacetime. So you mentioned Loon, you mentioned connecting the unconnected, you mentioned internet. Was Spacetime originally built for Loon? Maybe talk a little bit about sort of the evolution of the product. What was it originally envisioned to do? And I know you were working on it on the early founding team of that technology. So maybe talk a little bit about that.
Yeah, right. So when you look at this problem of connecting the unconnected, it's a problem that's like kind of highly related to population densities. Until these new rounds of like low Earth orbit and mid Earth orbit satellite constellations, you generally only connected large areas from one of two altitudes. You do it from like the height of a cell tower, or you do it all the way up at 36,000 kilometers into space in geostationary orbit. Geostationary satellites are great, but they can have like a third of the planet in their field of view, which can be like a third of the planet sharing their internet access. And then you're left with very few megabits per second per square kilometer. Like not a lot of data to go around. And then towers work great when there's enough money in the radius of the towers to pay for the cost of the tower. But in emerging markets or places that are sparsely populated, there's just not enough wealth in the radius of a tower to like cover the cost of building the tower. And for many decades, that's left a lot of people unconnected in the world. So when Google went looking at like, how are we going to connect all these unconnected people? Yeah, there's a component of it that was like subsidizing fiber deployment in Africa or other places. But a lot of the focus went to, well, how do we make communications happen for these other population densities? Is there a way to like affordably connect people in that middle area? And so we started looking at low Earth orbit satellite constellations. We started looking at high altitude platforms like Loon, unmanned solar glider drones, which Facebook was also looking at with their Aquila project. And when you look at all of those things, one of the things that you realize is, unlike towers and geostationary satellites, if you're in any of the altitudes in between, now the network is moving. People are used to networks where the users move. We all walk around with our laptops and our cell phones. We, the users at the edge of the network, are moving, and we're roaming between Wi-Fi access points and cell towers. But this part where the network is also moving, the infrastructure, the base stations are constantly moving around. That creates a bunch of challenges for networks. And so Spacetime, our software platform, was really born out of this need to operate networks in motion, not just support users in motion. And I think the part that was really unique, kind of happenstance, is that at Google, we happen to have space projects, multiple types of unmanned aerial systems and terrestrial systems that were all facing that challenge. So the part we did that I think no one really did before is we asked ourselves, can we solve that problem like comprehensively? Can we solve it once and let 4 internal projects all use the same solution?
Right.
Instead of doing what people have mostly done, which is like build pretty siloed vertically, like, stacked things.
So the original sort of mandate, for lack of a better word, was how do we figure out this kind of connectivity problem in general? But that sort of gave birth to this new challenge, which is like, we have all these different pieces of technology, but we don't have a connected software stack that like links all of them together.
We actually, like, when we were working on some of these different unmanned aerial vehicles like Loon, solar drones, and satellite work, we were all talking about how it would be kind of embarrassing if more than one of these projects succeeded at Google, but they couldn't use each other's ground stations, or like the users couldn't roam from one to the other. Like, we were Google, we should be able to solve that. And so the theory was internally, when we were setting out to build the software stack, it was like, well, maybe we could do twice as much work once, but build one system instead of 4 with like the 4 internal customers we had.
So talk to me about this kind of non-geostationary kind of network problem where, the users aren't just moving, but you mentioned, network in motion. So the network itself is moving. So talk to me a little bit about why that has become a bigger and bigger challenge over the years.
Yeah, right. So one of the hallmarks of these aerospace and defense and satellite communications networks is directivity, meaning like when you want to get a lot of data at a long distance, you focus the energy at the receiver. It's like the analogy I make for people is, if you're trying to talk to a friend that's like a long distance away across the room or outside, we all kind of cup our hands up to our mouth and we shout. And that's because if we didn't do that, we'd waste energy going in all directions. And we can talk, we can communicate better further if we focus the energy, if we shape the energy that we're transmitting at a finite power level, like at the receiver we want it to go. Aerospace and defense systems use directivity in wireless also for reducing the probability of intercept and jam and detect. So it's like the same reason you put your hands up to whisper to somebody. By doing that and shaping the energy away from them, you're limiting how much energy goes to unintended receivers.
Right.
So this is one of these big differences.
Versus like a Wi-Fi network, which is like,
yes,
spreading all over and can be easily detected and hacked and jammed and.
Exactly. Like your Wi-Fi, your cell phone, they're giving off energy more like a light bulb. The energy's going in all directions, which is great at short ranges, or if you don't have that much data to get through. If you're okay with low data rates, like for LoRaWAN or how your smart meter works, right? Very little data needs to get through. So it goes over long distances the same way, blasting the energy off in all directions. Those networks where the energy is going in all directions make them much easier for you to detect, like with the Wi-Fi networks nearby and have things join and discover, or for the networks to like self-organize. Devices can make a list of all the wireless devices they hear and tell their neighbors who they hear, and so on and so on and so on, to build a view and a picture of what's around. But when the beams are like really focused and shaped and narrow and directional, that doesn't work anymore, right? You need something in the network to be this sort of coordinating entity to tell the different beams where to point when, and when they should like change and point at something else, and what frequencies to use when, and how to route data across all of these things. So, you can just imagine in your mind aircraft or drones flying around if instead of light bulbs on them, they had laser pointers, right? And you can imagine an aircraft banks, and now the wing is obstructing the laser to another aircraft, right? You have all this changing geometry, all this changing motion, all these changing obstructions that create a lot of complexity for how you build and operate a mesh of those things. And cracking that was what we set out to do at Google, because we had 4 of them. And we thought, well, maybe we can just solve it once. But it turns out that by doing that, we solved it for all land, sea, air, and space. And we didn't really realize that our little microcosm in Google of having a satellite program, a couple unmanned aerial vehicles, some terrestrial stuff, was sort of this small microcosm of what, probably your listeners or readers of Tectonic and other things think about with like JADC2 and all domain networking for DoD. Like, the unification of land, sea, air, and space networks has been something that's been worked on for 40 years without being cracked. And we were working on it for a commercial reason of connecting the unconnected, and for just internal use inside of the Alphabet family of companies. But it turned out to have a lot of wide application.
Yeah. Okay. Well, there's a lot there we got to unpack. So we'll come back to this idea of the network in motion and how it relates to commercial and national security. And I know you're already talking about Tightbeam as far as your this technology goes. So let's pause on that for just a second. I do want to let's go back to Loon. So if I have my timelines correct, Google winds down Loon, I think, in 2021. You end up then taking a job at, I think, Facebook or Meta Connectivity. Then you hear that the technology has a second life. Talk to me about what happens there, because there was a brief kind of gap where you were working on the technology and then you weren't, but then you were again.
Yeah, that's right. And there was an amazing group of people, at Google and Alphabet and X, all worked to build the software that we now call Spacetime. And in Google, it was called Minkowski, which is, I don't know, the naming is sort of a reference that was Einstein's professor and the father of the concept of spacetime. And Project Minkowski was an amazing group of software engineers who started with a couple of us with the idea and kind of self-drafted into the project. We all started building it, and I think when we found out that that Alphabet was winding down, Loon, people move on and found new projects to work on. Some within inside Google and Alphabet. Others, went to other places. Some of our engineers went to Amazon Kuiper, or myself, I went to Facebook Connectivity. But I think universally, people looked back fondly and said, like, man, this is one of the greatest things I ever worked on. And I really loved this team. And so not only was it kind of my baby, and I missed working on it from something I really believed needs to exist for the world, but I missed the team that I was working with too. So at Meta, I was, I had left because they were winding it down, and there was an interesting opportunity over at Facebook Connectivity, which, by the way, that group is amazing over there too. Maybe people don't realize they build things and just give them away. They just open source everything to try to make connectivity cheaper for the world. They're building like open source cellular stacks, open source cellular radios, Wi-Fi systems, and just giving them away and open sourcing them with the Linux Foundation. So it's a pretty amazing mission. And I was over there working, and I heard from someone in Google corporate development, and then I also heard from our lead investor Arthur Patterson and my colleague and our current CEO and co-founder Chris Taylor, who were putting together an effort to spin the technology out of Google and acquire it with a new venture-backed company, which was really, really exciting. Of course, I jumped at the occasion to be part of that. I'll say the folks at Meta were just amazing about it. The process took a while. As you can imagine, Google's really great at acquiring things, but they can take a while to divest things. So they don't do that as often. So it took a bit to get that transaction done. But it was really exciting, and the team at Meta understood that this was a real passion project for me, and could not have been more generous about affording me the opportunity to see it through, and then understanding when I ultimately wanted to go and pursue it. And the last point I want to make about this is how humbling it was, where so many people from the original team were willing to leave, sometimes jobs they'd only been in for a short amount of time, to sort of put the band back together. Yeah, which was just really incredible.
Yeah, that's great. I mean, it kind of speaks to, what might on the surface sound like I don't want to call it I mean, it is on its surface even a complex problem, but when you get into like what it could ultimately do for communication and connectivity, I mean, it's pretty significant, which we'll get into. But I want to talk back. Let's go back to Tightbeam. So Tightbeam is more the hardware side of the company, and that traces back to what you'd mentioned earlier, Lawrence Livermore National Lab. Talk to me about maybe a little bit of that, and then how it all kind of comes together.
Yeah, there was an amazing guy named Tony Ruggiero from Lawrence Livermore National Labs, and I knew Tony, and he was a friend. He's passed away, sadly, but he was really passionate about solving this problem of making laser communications work well through atmosphere, and had spun the tech out of the lab. And Google had acquired Sierra Photonics, I think it was around 2013, 2014, and incubated this technology in the office of the CTO for a while. This was sort of more of a long-term bet. I mentioned we were working on Loon, and we were working on other unmanned airborne systems and satellite systems. And Google understood that if these projects were successful and they continued to scale, eventually the feeder links, the links back to the Earth, to the air and space layer, would become bottlenecks. And we see this now in commercial constellations and what's happening with mega-constellations like Starlink and Kuiper. And they see the same thing, that these feeder links will eventually need to increase in capacity and at some point become the bottleneck in sellable capacity. And said, hey, this is something we want to bet on and incubate for a while. It's interesting. Alphabet actually had two different laser communications projects. One of them in X, now Tara, was really focused on how do you do this affordably? How do you really make an impact in emerging markets with very affordable but resilient free space optics? This other group more came from National Labs heritage, pursuing aerospace and defense, quite exquisite, expensive, higher size, weight, mass, payload projects, but going for really high data rates. So nothing less than 100 gigabits a second through atmosphere was really the focus. And so when the transaction was occurring,
can you maybe just talk to me about the importance of that statement there, 100 gigabits per second through the atmosphere? I mean, that's fiber-like speeds, effectively.
Right. 20 gigs, right? 20 gigabyte file transferred in a second. Pretty astonishing data rates. But this is important for our industry because if you think about the trends going on, right? You want higher resolution imagery of the Earth. Right? It helps to be lower in altitude. You want to serve more megabits per second per square kilometer. It helps to be lower in altitude. But the lower you get, the more the satellites need to proliferate. We're going from hundreds to thousands to tens of thousands of LEO satellites in these constellations. And so what was a ratio of maybe 1-to-1, where each satellite had its own dedicated ground station, right? These ratios are changing. The world's 2/3 oceans, right? So we can't have a ground station under every one of those thousands or tens of thousands of satellites. We have to have inter-satellite links to route the data back to relatively few ground stations compared to the number of satellites. So take however much data these satellites are generating, whether they're doing imagery or earth science or communications, and then take the ratio of those satellites to the places that's economically feasible to have fiber to them to deploy these ground stations. Maybe it's 40-to-1. Maybe it's 60-to-1. Well, now you need 60 times the capacity, right, for the average data being generated per satellite for the feeder link, right, for that link back to the ground station. So you need these high data rates, right? It becomes more and more important because it has to handle the capacity now of 40, 60 plus serving satellites.
So my silly question is just going to be, if you had two Tightbeam terminals pointing at each other, that would be the equivalent of if you ran fiber, throughout those two distances, right?
Yeah, right. At 100 gigs.
At 100 gigs. Yeah, pretty interesting. Okay, so
we have photos on the website of this little ball, right? It's like the size of like a volleyball, like descending from the fuselage of an aircraft, and then spinning and locking with a terminal on the ground, and then moving data at these fiber-like speeds from 100 kilometers away.
Yep. Okay. So Aalyria forms. The band gets back together. Like, what's your kind of mandate as CTO, right? What's your mandate at that point?
Well, the first order of business is get the software running again.
Okay.
We built this stuff in Google to run on Google's internal infrastructure, which is like what Google Cloud runs on. And so when you spin it out and you get all your source code again, it doesn't even run. So first order of business is like bands back together, build the tech stack, get it running again, get it booting again, because start demoing to customers and start landing some opportunity, landing some business. And pretty soon we found both commercial and some government ones. Commercially with our partners at Telesat, who've been really amazing. And we had done some work with them when we were still part of Google. And then our first contract with the U.S. government was with the U.S. Defense Innovation Unit.
So Spacetime, you'd been working on for quite a bit within sort of the Google infrastructure. Tightbeam formed the Lawrence Livermore National Lab, but like as you guys form Aalyria, like how mature is Tightbeam at that point? Is it pretty much a
So I mentioned that the bet was made on Tightbeam, and a lot of the thesis is on this space to ground feeder links being a bottleneck. But in the history of those 7 years at Google, the space projects we were working on, were wound down earlier. And the ones that lived the longest and saw production deployment were like Airborne or Loon. And so when it spins out, we get one of Google's test aircraft. We've got a building with our labs, but it's an airborne terminal, right? It can be mounted on aircraft. We have air to ground links and demonstrations and hundreds of flights and landings. But you could consider it something that's probably like TRL 7 or 8 sort of thing. It's like sort of on its 5th generation at that point. We're now on our 6th generation of terminals there. So pretty mature test ranges that run all the time. But work to do to spin another iteration of terminals to make them even better, even more resilient, to be able to survive even more atmosphere. We want to integrate them with Spacetime so that Spacetime's sort of the brain, the network operations system that supports anyone's hardware. But certainly now that we're a combined company, you want your hardware to kind of come with the printer driver for the operating system, so to speak. You want it to be plug and play for your customers. So doing the work to hook that up.
Yeah, so that's a good way to put it. Okay, so let's take a quick step back, especially for anyone who might be listening who might be lost, which actually I think you've done a great job so far. So hopefully that's not that many people, or hopefully it's none. But okay, taking a step back. So Spacetime really is the software orchestration layer for all of these different networks that run on all the different types of source code, which we'll talk about in a second because I do want to get into that. And then Tightbeam is the actual terminal that then you can use for specific communication. Why can't current satellite and defense networks do what Spacetime does right now? Like what is the breakthrough, and how has it been done so far?
Yeah, I mean, obviously people operate LEO and MEO constellations today that don't use Spacetime, right? And the way that they're doing it today, and the way they always have done it, is by usually having the spacecraft manufacturer build custom software that they deliver with the satellites that is hard-coded in the source code to leverage what simplifications they can about specific orbits, specific frequencies, specific antennas. Maybe if you're a MEO constellation, you just go around the equator, that geometry just keeps repeating. So the schedule could repeat forever, but that's not true in LEO constellations, for example. And so if you can use that simplification, you'll take it. These things are complicated enough, right? Everyone has enough risk on their hands when they're building a system like this. And so every person that's building one of these networks is embarking on a sizable engineering team to build and deliver to whoever's going to operate the network the brain of the network that's coded for that network. Okay. What's the downside of that? The downside would be, one, this is an investment that everyone has to keep making over and over again, right? Which just adds costs and increases barriers to entry in our industry. But the second problem is that when you're trying to unify these networks or make them interconnect with each other, right? I've noted to others that like the DoD has had slide decks that have icons of planes and ships and satellites with little lightning bolts between them, proposing the unification of land, sea, air, and space networks, and hasn't pulled it off for a long time. We attribute kind of the primary reason for that is that all of the systems and platforms that they've procured have come from prime contractors with these bespoke vertically integrated, hard-coded operation systems and brains that only work, for those fleets of equipment, with those obstructions, with those antennas. And when you want to say, okay, I need these two systems to both analyze when they could communicate, when they could point a radio or a laser beam at each other, when they're flying past each other, and schedule a moment to like tunnel into another one's network and tunnel across it. Like they can't. They only know where their obstructions are. They don't understand where the other vehicles would be. They don't have a way to speak the same language to each other to exchange information about such things. And so one of the things that's really changed in Aalyria, in our business, since spinning out, in our engagement with the market, is that while people very much appreciate the opportunity of like buying a system and not having to build it again, the part that's been an even bigger unlock recently has been the power that unlocks for their networks to talk to other networks and to broker when they could federate or interconnect and tunnel across each other to do networks of networks. It's sort of like a secondary benefit, and it's a true network effect.
I'm not an engineer, so I'm sure you can get very technical on this next question, but I am curious, like this whole kind of dynamic of having different architectures with different source codes talk to each other without modification is pretty significant. How do you do that without modification?
Yeah, a lot of it is taking the problem more down to a physics level and to like a first principles level. And we actually kind of drew inspiration from the data models used by tools that some of your listeners might be familiar with, like the product STK from Ansys. We don't use STK, the Windows application under the hood of Spacetime. But what's really impressive about what those folks did is they have an open way to model networks in a general way about transmitters, receivers, antennas, filters, amplifiers that let you sort of stitch together as someone trying to simulate a space network and do analysis on it. Other tools used in the networking industry to do modeling and simulation of like cell phone networks, Wi-Fi networks. They allow researchers in academia to experiment with new standards and not have to build the networks for real. And a lot of them have built kind of ways to model networks. So we had like a team of people who had worked in the modeling and simulation world of both wireless and computer networks and aerospace, and said, okay, like how do they come up with something that's both general but detailed enough to be able to do all the math you need to do to analyze like time dynamic geometry and signal quality and stuff like that, and to simulate networks with high fidelity. And we sort of built a large scale distributed system the way Googlers would build it, of like hosted on Kubernetes. It runs in a cluster. It's got a bunch of microservices. It's built on best practices. And like we built something very scalable, right? Unlike the applications that maybe we drew our inspiration from that can run cloud native and very scalable to pull this off.
So when a customer says, okay, this is great, right? Someone might be listening saying, this is awesome. I want this. Like, how do you think about like, but like they'll say, well, I have my own network and I have my own system. How do I integrate it? I'm assuming that, I have to feed my entire network through kind of some software API into your data model that then takes a bit of time, training and integration before it's all up and running. Like, what does that process look like in practice?
Yeah, the first thing is that our system's all what they call single tenant, meaning we don't try to have some SaaS platform that has every customer's network in it. What we've learned is that people building multi-billion-dollar aerospace and defense networks usually have some opinions about where the brain of it lives and runs. They want to have the keys to the encryption. So the tenancy of it is all dedicated. Our government customers will want it running in classified clouds that are air gapped, right? Our commercial customers are fine with it running in commercial clouds, but might want it to have data sovereignty turned on in a certain country where they're based. And when we spin this up for our customers, there's like that initial step where, okay, I've got to sort of onboard my data into this open model. One cool thing we did is we open sourced all of that. Like the data model is completely open. It's up on GitHub. A lot of it even lives in like a neutral nonprofit called the Outernet Council that we stood up. Because sort of like Tesla opening all of its patents, right? Like we want to. Our bet is that we can out execute, out innovate, outpace on velocity. We don't want people worried about vendor lock. If they don't feel like Aalyria has done a good job in the role that we're playing in the network, we want to make them feel like they could replace us and drop something else in that speaks the same interface, right? The benefit of that is that we get a whole ecosystem starting to flourish of people that make satellite modems and antennas and ground stations, people that make enterprise software that build integrations across these interfaces, which is cool. So we value kind of the open royalty-free network effect of that more than a strategy that would sort of lock people in to proprietary interfaces. But yeah, we sort of spin up these instances. We partner with the company, kind of onboard all their data. Then the system lights up, and usually they get to kind of witness through their web browser this visualization of their network flying, kind of peeking years into the future, seeing what it would look like as if it were already operating in space, and seeing that it does what we claim, feeling that they can get the trust in it to kind of trust it to do the job.
So switching to the hardware kind of side and Tightbeam, when you say 100 gigabits per second through the atmosphere, over long distances, maybe, also talk to me about what long distances mean, but also like, what's your reaction when you demo that to customers?
Yeah, that one's pretty fun. Yeah. The way we tend to demo that is we bring people out to our headquarters, which is in Livermore, California. And we have a laser gimbal on the roof, right, of the building. So it's installed there. It's got this like laser head. And then there's another one on the top of Mount Diablo. We have a couple other ones in the area at like observatories, in the San Francisco Bay Area. And then we have our own plane that will take off and start flying, like doing figure eights and loops over the North Bay. And you can see the laser terminal kind of snap and acquire, within seconds. We have a traffic generator running in the lab. And then you see the data rate, like, peg, to 100 gigabits a second, moving data at that speed, which is pretty cool. And we'll actually at times during the demonstrations, either cue the pilot or have someone on the ground break the link on purpose, like make the pilot bank at a geometry that'll cause an obstruction from the wing or something. Spacetime will anticipate that before it happens because it's looking at the changing motion. And if there's a handoff that can be made, it'll do it preemptively. And if we force it not to do it, you'll see the link break, and then you'll see it reestablish very quickly. And there's a really fun wow factor to bringing customers and VIPs out to witness.
Yeah. Was there any specific person? You don't have to tell me the person, but specifically who the person is. But was there any type of person figure? Maybe it was a scientist, an academic, someone in the military, where you were like, you surprising them was like, okay, we got something here.
Yeah, for sure. I mean, it's often like you see their mind kind of changing. One of the first reactions they say is like, okay, we have an upcoming acquisition or something. And often then we point out to them that because of our relationship with the Defense Innovation Unit, we have this amazing contract vehicle, right? And for any of your listeners that don't know, one of the awesome things about the U.S. Defense Innovation Unit is they sort of create this speed ramp. Like once you've done a successful prototype and demonstration with them, and they've been amazing partners, it makes it very easy for anyone in the U.S. government to sort of buy the technology sole source. And so that the first reaction is, wow, this is amazing. We should think about how we could even buy it. And then when you say, hey, actually, you can. We already have this like special paper and special demonstrations and test results that allow anyone in the U.S. government to get to it very easily. Then that's actually where the reaction, they sort of sit back in their chair and they go, wow. Because you can see them rethinking what that now means to their organization, that it's just now a matter of political will and like an institutional inertia that would keep them from doing something radical.
Well, so let's talk about that, right? JADC2, you mentioned it earlier. Like the government deeply cares about this network of networks, and it's obvious why we're multi-domain, lots of different vehicles, people needs to talk to each other. What has been the friction so far that has prevented that from happening? Is it technology? Is it politics? If it's technology, then it's like, okay, well, you guys have a really good potential foot in, shoe in to be able to be that provider. If it's politics, then obviously that's a whole other ballgame. Maybe it's still a mix of both. But like, how do you think about that? And because you guys are selling into government, you're having these conversations. Where does it all stand?
I think until 3 years ago, it was technology. And maybe until 2 years ago, it was still technology, because just because we spun out doesn't mean we were in a great position as soon as we were born to demonstrate it all, to the right people and the right audience with convincing demos. We're past that now. For the last 2 years, there is a high degree of customer education component to this. Like, probably you and your listeners can appreciate, like, this stuff takes a bit to get your head around. That's one of the things I really appreciate doing this podcast, because it gives us the sort of medium to really explain these things to listeners. This is hard for someone in the U.S. government to digest in a 30-minute meeting or a 60-minute meeting with a lot of people in the room with slides. It takes a few times for it to sink in. It takes sometimes for them to fund a study or a demonstration to witness it and then be convinced. These things have their own timescales, right? To even get a prototype or a study or a demonstration, and then for those things to be procured and for those results to come in and then be analyzed and be convinced. So I think it's sort of breaking wide open in our favor right now, and that's really reflected in our successful raise in valuation. We have a lot. It feels like finally a lot of that is opening up where it's clicking for people. They're getting it. And that the synergies of that network effect, are starting to occur. What we see two big use cases in public sector that are driving that. One of them is affordable resilience for the warfighter from a SATCOM terminal standpoint. They want to be resilient to the outage of any single commercial or government network, right? Like, everyone loves Starlink; it's amazing, but you still have people that say, "Hey, I want to have a backup to that. I want to be able to switch to, maybe one or two other networks. Maybe I want to have three, in my wheelhouse that I can switch between if any one of them goes down." But they can't afford to triple the bill they're spending on Starlink. And so a lot of them are thinking about how to do that, how to have affordability and resilience. And what that ends up looking like is being able to dynamically ask those networks to broker or provision service to you, or to change your tier of service dynamically, which involves those software interfaces we were talking about earlier, those networks and networks interfaces. The other use case that comes up with our customers at NASA or in DoD or DOW now is in-space interconnect and transit. So like, when you have a government satellite in space, maybe they don't want to rely exclusively on government ground stations. They might want to not only use commercial ground stations, which has been around for a while, ground station as a service, but also maybe like relay in space through radio or laser links to commercial satellites and tunnel across them in space. And that's sort of the other use case.
Have you tested a Tightbeam terminal in space?
No, that's one of the things that that we aspire to do with some of the funds we've raised. I was talking earlier about how the later years at Google were really focused on unmanned airborne systems, and so we have a system that's quite mature. But haven't yet got a chance to form factor it and have a space terminal really engineered around that environment, and to put one on orbit and test it, which is one of the things we aspire to do. I will note, though, that it's interesting. The ranges, when I say 100 kilometers, you're like, well, isn't that pretty far off? You got to go 800 or 10,000 or depending on your altitude to space. We actually go through more atmosphere now successfully at 100 gigs than we would need to go through for space. And that's because the demonstrations we do, if folks visit our headquarters or see a demo, they're very low elevation angle, right? They're ground to ground or ground to mountaintop or ground to low altitude aircraft. And the atmosphere's thickest closer to the Earth, right? So these, just single digit degree shots, from the roof of our building to the top of a mountain at less than 10 degrees, this actually has like more total atmosphere to get through than if we were pointed straight up to geo.
Well, is there any technical reason why your space terminal, like a space version of the Tightbeam terminal, wouldn't work? Like, is there any? What's the technical risk now where you put a terminal up and you're like, oh shit, this doesn't work?
A lot of the IP we have is transferable, like things where there's adaptive optics or deformable mirrors or novel sensors. And I shouldn't get too deep into this because I'm not the expert in the company on the optics and photonics. My colleagues are. And all that IP is very transferable that we know. There's parts though that are different challenges that exist in the link between Earth and space. One of them is diffraction, because um, when you hit the atmosphere, it bends the light a bit, and there's a lot more total distance for it to travel already bent. And for your listeners, this is kind of neat. One thing I didn't understand intuitively at first either. The link from space to Earth is easier than the link from Earth to space. And that's because the link from space to Earth, the laser has traveled like the vast majority of the distance it needs to travel before it hits the atmosphere and gets bent. And so it's easier to catch the light in the bucket. But when you go in the other direction, you encounter the atmosphere earlier, and then it's traveling the vast majority of the link distance already diffracted. And that makes it harder to catch the light in the bucket on the other side. You have to like do a lot more pre-compensation for what the diffraction is going to be, when you transmit. And so that's another thing to watch for, and where this leads the industry. And you got to kind of watch this when you see marketing materials that a company, demonstrated 10 gigabit laser comms from orbit or 100 gigabit laser comms from orbit. Is a lot of them are only doing that in the space to Earth direction, right? It's much harder to do the Earth to space direction. And what that means is that's the difference between unlocking the use case for Earth observation, where you're mostly just sending data collected in space to the Earth, right? You're generating data collected by imagery from synthetic aperture radar, from something else. You're transmitting it down. And then it's fine. That's the only direction that you can do it very well at. But when you want to support internet communications constellations, it's actually more important to do it the other direction. And the reason is most of us download more than we upload, right? It's changing a bit. Like, when we're doing this podcast or we're doing another application, it's more symmetric. But on average, most of us download more than we upload. If you use cable modem internet or something, right, it's always like 50 megabits down, 5 megabits up, things like that.
Yep.
Right.
Yep.
And so for you to support that on the user side, you have to be able to send more data up on the feeder link than you pull down.
Yeah.
Right. Because it's a forward direction.
So I want to talk about adoption a little bit, right? Because like for Spacetime to work as this kind of like godlike orchestration layer, you probably don't like that I called it godlike, but some type of orchestration layer around all of these different technologies, right? It needs to at some point turn into some type of standard, right? It needs to become a common standard. Like, do you like? And tell me if you disagree with that. Like, how do you see that working in practice, especially when you're talking about? I mean, like again, going back to JADC2, like you're talking about these primes, right? Where it's like not going to be easy to like integrate with those primes. Like, how do you think about how this becomes a standard?
Yeah, and what we've been evangelizing is our product does not need to become ubiquitous and a standard. Of course, we'd welcome that commercially, but we think that's an audacious thing to say, is that for the world to solve the internetwork of networks in motion, and for the world to kind of unlock the internet of flying, moving things, everyone has to use this one product. Like, I don't think that would point to maybe a flawed architecture if that was our assertions.
Are there other companies that are?
So, well, instead, what we've done is we've said, no, let's make the interfaces open, right? The APIs, the language that these things use to speak to one another. And so rather than a single godlike orchestrator, you can think of the actual architecture is that each network gets its own brain, right? Its own, orchestrator. And we kind of define compass directions, if you will, north, south, and then like east/west. North means the interface that enterprise and mission applications use to talk to the orchestrator. So this, in a defense construct, this is like the battle management layer says, I need connectivity from this warfighter to there, or I need connectivity from this sensor to this shooter. For commercial internet, that's the system that keeps track of who's paid their bill and who's bought what tier service. It says, hey, I need 50 megabits down, 5 megabits up from this house to the nearest internet exchange point. That's our northbound interface. The southbound one is the one that talks to the antennas and the satellite payloads and the ground stations. And then the east-west one is what allows those brains to talk to other network brains, to let the network operations system, another network operations system of a third-party network, or any number of third-party networks. So that's sort of the Spacetime talking to Spacetime, right? NASA's Spacetime instance talking to Telesat's Spacetime instance. Because all of those APIs are open, anyone can build integrations to it. but it also means anyone else can replace us if they want to. And for the northbound and the east-west, our APIs, I would say, are the best, kind of the only standard, at least being tabled, that supports all the use cases we've discussed. For the southbound interface, we offer two flavors. One is the one that we developed at Google and have open sourced. And the other one is the O-RAN interface for 5G and 6G non-terrestrial networks, which is a fast emerging standard that's just starting to get adopted.
Yeah. Can you maybe at a high level just talk to me a little bit about the work that you're doing in the defense industry specifically? I mean, you're working on a number of times. You mentioned DIU. I know you're doing work on the hybrid space architecture. Like at a high level, tell us a little bit about what you're working on.
Yeah, the hybrid space architecture is an initiative that's really chartered with facilitating the internetworking of U.S. defense, intelligence community, civil space exploration agencies, commercial space companies, and allied governments. So it's really anyone you can think of that's operating a space network. And making those things interoperate and internetwork, there's a few dimensions to it. Some that we aren't solving, like making laser terminals compatible with each other. Like right now, Amazon and SpaceX and different laser terminals and different spacecraft aren't compatible. There's efforts outside of Aalyria to come up with a common standard or have translator satellites that intermediate. There's other ones to have the radios be interoperable, like 5G and 6G non-terrestrial networking and other virtualization projects going on. But the component that we're working on is these software interfaces, right? To let the software that orchestrates one network be able to talk to the software that orchestrates another, and to have open software interfaces so that anyone can develop and plug in and develop hardware. And so our work with the U.S. Defense Innovation Unit has sort of had, a dozen or more other government offices and agencies who have signed contracts with Aalyria to do paid pilots and demonstrations, some of which now are transitioning, towards production work. And then we also had a successful pilot with NASA recently for their near space network.
And then what about on the commercial side? I know you're doing some work with Telesat Lightspeed.
Yeah, right. The Telesat Lightspeed constellation is a low Earth orbit satellite constellation, fully funded. Launches are scheduled and manifested, so it's very real. And we've already delivered Spacetime, continue delivering at a steady cadence to that customer, adding all the additional features needed for their network, which has some really novel attributes, some of which are pretty neat. Things that are even differentiated over Starlink. They're really targeting enterprise, like medium to large enterprise, I think. Don't want to speak for them. But Telesat Lightspeed has this cool property where any terminal on the network can create connectivity over the laser mesh to any other terminal without going through a ground station, which is really neat. I don't think Starlink supports that. So, like, if you had a bunch of ships at sea, for example, that wanted to make their own private LAN, they could form that over the Telesat Lightspeed laser mesh without ever touching the shore, which is really cool. And you probably imagine that any-to-any routing that we have to solve with Spacetime is more challenging than solving the routing where all the traffic goes to and from a ground station.
So, with the remaining time we have left, I want to talk about the funding round and what's next. So, you raised $100 million, $1.3 billion post. I think Google is still retaining a stake in Aalyria, a minority stake. My notes here have Battery Ventures led the round, and then J2 Ventures and Dine are a couple other investors who participated. I'm sure there's others, but tell me about that round. And I know you mentioned Arthur Patterson in the beginning of the conversation, which I assume this is the Arthur Patterson who founded Excel.
Yeah, that's right.
So you have a good group of investors now around the table. But yeah, tell us about the round. Like, how did it come together, and where is that capital going into over the next couple of years?
Yeah, right. We're really excited. An amazing group of investors, and they've just been wonderful. And everyone brings different perspectives that are all valuable. And we have an amazing board of advisors as well. Vint Cerf, the father of the internet, other really notable people, senior backgrounds in the U.S. government and elsewhere. So we're really blessed that between our investors, our board of advisors, just like couldn't have better support. In terms of where we're using the capital, you kind of think of it in maybe a couple broad categories. One is on the Spacetime on the software side. We just need to scale the team. I think generally our team is like been waiting for this round to close because we've been managing cash and burn as a startup does, until this next tranche of investment, and needing to staff up and hire. We joke that we're sold out of Spacetime. That each of these onboardings and these trials, it's like, okay, when you get to the point where you're trying to time phase your next trial to be able to support the onboarding of the customer, that's the inflection point I think every investor wants in a Series B, where you just need to scale because the demand's so high. Of course, there's new features for 5G and 6G non-terrestrial networking. If any of your listeners are going to be at Mobile World Congress in Barcelona, we'll have a booth. Stop by. There's going to be an awesome demonstration of Spacetime integrating with real vendor non-terrestrial networking, 6G, 5G base stations. It's super cool. So that's where that capital is going on the software side. On the hardware side, it's to support our existing contracts with some of our pilots of Tightbeam, with some of our government customers, but also to expand the use cases. We talked before about how we aspire to do the space to ground and ground to space links. There's work there, and then there's also work to demonstrate air to air, air to sea, land to air to sea, these sort of use cases with some of our customers there too. So it's sort of to expand the breadth of what we're doing with laser communications through the atmosphere.
What are the next kind of big milestones, whether it's contractual or technical, that folks should be looking out for?
Yeah, I think there's a couple neat ones. We're looking to really kick off some of the demonstrations at scale of the hybrid space architecture really soon. This ability to dynamically coordinate, whether in space interconnections and relays, or between hybrid SATCOM terminals and different satellite networks, to kind of make the roaming experience feel a lot more like what roaming feels like on all of our cell phones, where the adjustments of service plans or the provisioning of connectivity happens within seconds to minutes. You don't have to sort of pre-buy a monthly or annual plan in order to roam from one network to another when you didn't plan it in advance. We're looking to really demonstrate that at scale and make it durable, have it be things that we leave on for us and our government partners for use in all the different operational exercises the government has. We're excited about our work with NASA and the work we're doing there. And I think there's things that we have going on that should result in announcements soon about some definitive uses by some of our customers.
What keeps you up at night?
Yeah, I mean, it was this race, right? It was until now, of course. Everyone wants to get the raise done so that we can turn it up to 11 on scaling. And now we're there. So we got a new set of challenges now. It's maintaining our talent density and our high bar for talent. One thing I care a lot about is our engineering pedigree and our culture at Aalyria. We have this great group of people from top tech companies that, and I think we're able to do a lot with a relatively small team because of that talent bar and culture. And so scaling quickly, onboarding people without breaking that culture is a new set of challenges. And I think that's what I'm thinking most about right now.
What's the long-term vision for Aalyria? Call it 10 years from now, like assuming you guys execute well, what does the business look like?
Yeah, well, I think if it wasn't obvious to folks, the laser communication part of Aalyria and the software side of Aalyria are actually, I think, much more synergistic than a lot of people realize. The part that's intuitive to everyone is that laser communications between Earth and space only works if you can change the ground station when there's bad weather at one to use a different optical ground station where the weather's better. But the part that a lot of folks miss is that when you do that, sometimes the laser needs to change to use an adjacent satellite for that link that it didn't use before. You move the ground station 1,000 kilometers to the east or to the west to find better weather. Sometimes it's to a different satellite than before. And when you do that, all the inter-satellite routing has to change in space. The allocation of users to user links change. You can't go to market with optical ground stations without Spacetime or something like it being a platform used by both the ground network and the customer in space. Maybe those are the same organization. Maybe they're different organizations in some business models. So I think when you look to say, where is Aalyria going? We're going to bring those things together in the future to make that reality possible for our customers. And we're also going to do more work helping these constellations and airborne networks be able to better coordinate with one another for more efficiency.
When you're not figuring out network orchestration and laser beams, like what do you do for fun?
Most of my time outside of work goes, to trying to be a good father and husband. I've got 3 young kids. They're 8, 10, and 12 years old right now, and so it's a busy phase of life, but a very enriching phase of life. I've got lots of sporting events to go to, and hanging out with some good friends and families in the area. So, yeah, mostly that.
Well, that was a great answer, but I still want to hear a hobby. Like, give me a Brian hobby, like something that like maybe not a lot of people know about.
Okay,
that you enjoy doing.
Yeah, I've been getting into trap and skeet shooting lately.
There we go.
Yeah, so if anybody's in the area, would enjoy that. Actually, at one of our investors' annual investment summit, wouldn't even know it, but at the end of their annual summit, they announced that they had a shooting event afterwards for all the LPs and the founders, and I think it was something they didn't know about me. So I went out and ended up getting top on the tournament, which I'm not that great of a shooter, but I think it was just everyone else was even worse. But I joked with them last time that next year they should make they should put some stakes on it, tie some investment or secondary to it or something like that.
Exactly. No, that's great. That's good to know. Well, well, for anyone who's into skeet shooting, definitely link up with Brian.
Yeah,
I've tried. I'm not very good, so I would say maybe me, but I don't want to embarrass myself. So, Brian, thanks so much for being with us. It's great. I know this is going to be a complex topic, but I thought you did a great job going through all of it in detail and in a way that I think makes a ton of sense. So, very excited for what you guys have built. Congratulations on the round again.
Thank you.
And excited to see how the company develops and have you back in the future.
Sounds good. Thanks, Mo.